Okay, so this is going to be a shorter video on combustion analysis, and it's one of those things where it's good to know about and to understand relationships. Again, I'm not, unless we have an abundance of time at the end of the topic, I'm not going to have you go through and do a lot of combustion analysis problems. Okay, so in combustion, but this is something you do need to know, is what is combustion? Okay, so combustion itself is a type of chemical reaction. And we kind of studied that before when we talked about chemical and physical change. What's a chemical reaction? How do you know you have a chemical change? So combustion is one that is a type of reaction you need to have memorized. You need to be able to predict. You need to be able to balance. And then from there, you need to be able to calculate mathematical relationships. Okay, we'll take it in steps. So combustion itself is taking any usually organic compound, carbon containing, you usually have hydrogen and oxygen in there. We don't do a lot with nitrogen combustion, so it's mostly CH and O that you're asked about at the AP level. When you go on in chemistry and you talk about reactions, then you go and do things that contain other elements besides carbon, hydrogen, and oxygen. So you take any compound, and in order to have combustion, you have to have oxygen. Because otherwise, it starves and the fire doesn't go. Because combustion is burning. And for the sake of AP and even Regents, we talk about it going to complete combustion. And complete combustion is CO2 and H2O. Okay, so that's when your combustion is complete. Now, there is this thing called incomplete combustion, and incomplete combustion gives you CO and H2O. That's why you need carbon monoxide monitors and detectors if you have anything that is gas related in your house, like a stove or a furnace, or if you have a gas fireplace. You should have a carbon monoxide detector, because the burning of that organic fuel of methane, which is natural gas, with the oxygen can give you carbon monoxide, because not everything goes to completion. Okay, now we are going to focus on this equation because you will use up the O2 and you generate CO2 and H2O. But how much you generate of these relates back to that. And the reason being is called conservation of mass. Right? Conservation of mass says whatever you start out with on this side as mass combined has to equal with what you produce on that side combined. Because you have that relationship, and I'm going to start stressing now, that relationship, this over here equals this over here, is how we do a lot of things in chemistry. So not just combustion, but we're going to do stuff called gravimetrics, stoichiometry, prediction of yield. That all has to be related to how one thing on one side relates to the other thing on the other side. So we use the relationship of moles to know that in CO2, I can figure out how much carbon was in the original material, because there's carbon here, and it's going to generate the carbon in this thing over here. And I'm going to erase this so you can see what I mean. Okay. The carbon in this compound here comes from the carbon in that compound there. And so if I know how much I have here, I had to have this much, because it's not going to be created out of the air. It has to come from here. The same thing for this. The hydrogen in the water, molar ratio, right? I have 2 atoms of hydrogen per molecule per mole of H2O. Okay? And I have 1 carbon in each CO2. So if I know what I have here, I can back calculate to what I started with over there. And if this compound here has any other element in it, and in our case it'll be oxygen because we're not doing nitrogen burning, then the mass of this compound minus carbon minus hydrogen will give me my oxygen. So it's all related. So if I know this grams, so if I go back and say, okay, if I know X grams over here, I have so many grams of it. And I'll call this Y grams, and I have so many grams of that, I can back calculate. And this is how we do it. From the CO2, you calculate the moles of CO2, and then the grams, then you're going to go to moles of carbon, and then grams of carbon. So in carbon dioxide, there is 1 mole of carbon. If you look at a whole mole of CO2, you have 1 mole of carbon and 2 moles of O2. And you might say, no, you only have 1 atom and 2 atoms, but we can also call that a molar ratio, right? Because an atom weighs very little compared to the mass of a mole of it. But when you look at the ratio, 1 to 2, it stays the same. Definite proportion, definite composition. Okay? Here, if I know I have H2O, every mole of water gives me 2 moles of hydrogen. So you go back and you calculate backwards. So I'm going to erase this so we can look at the problem, because I've written all over the problem. So I'm going to take this away. Okay. Now, in the problem, it says the substance weighs 0.1156 grams. And it just says this one only contains carbon and hydrogen. And it does say we're burning nitrogen with it as well. So we're not going to worry, because over here there'll be a nitrogen containing compound. We're only going to focus on these two, and we're going to go backwards to that. So in this compound, though, there's nothing else. There's carbon, hydrogen, and nitrogen. Okay, you could also have carbon, hydrogen, and oxygen. One of those two ratios, one of those two types of mixtures, like not mixtures, compounds. Right. So when we burn it, and I'm going to change my little color here, we get 0.1638 of CO2, and we get 0.1676 of water. So now we're going to go and back calculate. We're going to figure out in this mixture that we have, or it's not a mixture, I keep saying a mixture, but it isn't. It's a compound. That's the starting mass. And the compound contains C, H, and N. So we go backwards. If I know how much CO2 there is, I can find moles of CO2 by converting with the formula weight. Okay? So this is the formula weight. We're going from grams, so we cancel out our grams, so the grams go on the bottom, 2 moles. I know that 1 mole of carbon exists for every mole of CO2. And then if I need grams of carbon, like sometimes they ask you to stop here, and you can get, if it's just carbon and hydrogen, and you don't have to worry about another element, you can stop there because you can do the ratio between carbon and hydrogen in moles. But if you need to find a third element, then you have to go to grams. So I'm just going to put over here, if it's only C and H and nothing else, okay, you can stop at moles. But if there's a third one, so whether it's nitrogen or oxygen, you have to go to grams. And I'll show you why. So this back part will always stay the same for every single problem, going to grams of carbon. And you find your number of grams of carbon. Do the same for water. This is the mass of water that came from the problem up above, 0.1676. So, and I'll highlight it in blue so you know that came from up above. This was orange, but it really kind of darkens it, so I'll leave it alone for the other element. And now we convert it. This is grams H2. Now, I have one thing that's left, and that's to find how many moles and how much N I have. Here's my starting mass. I subtract the carbon, I subtract the hydrogen, then I get the nitrogen. Okay, so whatever you start with, if you have a third element, you have to subtract the mass of the carbon and hydrogen from it to get the third element. The third element could also be oxygen. Okay, I can't go down any further, so I'm going to reopen the window in a second. Come in. So now I do it as if I'm calculating an empirical formula, which we did up here. It's the same procedure. I get my moles of carbon. Now this is where I said you can stop. You can stop right here and write down your moles of carbon if you really wanted to, and then go to grams. Or that was hydrogen. Carbon was here. But you can say, oh, I'm going to do this calculation, and then I'm going to write down my moles of carbon. I'm going to do this calculation, and then I'm going to write down my moles of hydrogen. I just went back and said, oh, I didn't stop, so I'm going to have to find the moles. So I calculate the moles. So this is step 1 and 2. Okay, and this is step 3 and 4 of doing your empirical formula. All right. So, again, this was our carbon. This is our nitrogen. This is our, whoops, I did the wrong thing. That was our hydrogen. I don't know why I put nitrogen there. That's my hydrogen. This is my nitrogen. And you go through and you do your normal empirical formula calculation. That's combustion analysis. That's how you do it, step by step.